Okay, let's talk about distinguishing solid, liquid, and gas phase of a pure substance. This is an ALEKS topic that a lot of folks seem to be having trouble with, and I'm hoping I can help you. There are a few aspects to these problems that are always the same. They always tell you the substance that you're talking about. They always tell you the melting point or melting temperature. And they always tell you the boiling point or boiling temperature. Okay, now they also represent their substance using a space-filling model. Okay, in this particular example, they're using sulfur dioxide, which is going to have 2 oxygen atoms and 1 sulfur atom. Usually in these type of models, sulfur is represented by the yellow particle and the oxygens are red, and both of the oxygens are attached to the sulfur atom. And so you get this kind of Mickey Mouse looking shape. That is the shape of an intact molecule. If they were to represent the particles in their models as a separate dots of different colors, what we're talking about now is atoms that are not bonded. That's what their model would mean at that point. Okay, so I want to talk a little bit about what's going on. All right, they've given us a melting temperature and a boiling temperature. What does that mean to us? Well, substances conform to what's called a heating curve. And substances have a melting point and a boiling point. So let's assume that our sample was water for a moment, and I'll walk you through what this means. This graph shows a heat entering our substance at an unchanging rate. And this axis is temperature going from low to high. Okay, so we can start with a piece of ice at a very low temperature, and we can start adding heat to it. As we add heat, the temperature of the ice will raise until it gets to the melting point. Okay, for water ice, that temperature is 0 degrees Celsius, but we're not dealing with that in this particular example. But I'm going to use water to help you to understand this. Okay, so we get to 0 degrees and our water starts to melt. In fact, we continue to add heat to the water for all this amount of time, and we are not seeing a change in temperature. All that's going on here is a phase change. We're changing phase from solid to liquid. All right, once all of our solid has turned to liquid, then as heat continues to enter that system, the temperature of our liquid rises and rises until it reaches the boiling point. All right, and as our liquid vaporizes off, we're inputting heat, but we're not seeing a temperature change. We're seeing a phase change instead. Once everything has been converted to vapor or gas, that gas can also rise in temperature with the input of heat. Okay, so going back to our example, for sulfur dioxide, they're telling us that the melting point is negative 72 degrees Celsius and the boiling point is negative 10 degrees Celsius. Okay, and now we have to look at our examples A, B, and C and figure out which drawing goes with which sample. Okay, so sample A, we're given a temperature of negative 32 degrees Celsius. We have to ask ourselves, where would this fall? If on our graph this was our melting point, and this was our boiling point, well, where does negative 32 fall within that? Is it lower than the melting point? Is it in between the melting and boiling point? Or is it higher than the boiling temperature? Well, negative 32 falls in between the numbers -10 and -72. Therefore, this sample must be a liquid. And I'm going to look for a model that reminds me of a liquid and how the particles would look if we could see them. Okay, all right, I'll get to what the models look like. Let's do the next one. Okay, in this one, we've got a sample at -104 degrees Celsius. Again, we've got to decide, is that temperature colder than -72 degrees? Is it in between -10 and -72 degrees, or is it above -10 degrees? Well, of course, -104 Celsius is below -72 Celsius. So we're going to find that this one is in its solid phase. So we're going to look for a particular kind of model to go with that. Okay, last one before we go on to the models. Last one is C. And C says positive 76 degrees Celsius. Okay, again, we decide. Is it below the melting temperature? Is it between the melting and the boiling temperature? Or is it above the boiling temperature? Well, positive 76 degrees is well above our boiling temperature of -10. So this one is definitely going to be a gas. Okay, so now what we're asked to do is click on the slider and select which of the drawings 1 through 5 best represents this substance in this condition. Okay, so what are we going to look for? Well, for one thing, solids, we will see the particles are orderly and they're touching each other. Okay, so we're going to look for a nice organized display of those particles. They're all touching each other, neat, tidy, and packed together. Okay, a liquid, we're going to see the particles close together, touching, but we will no longer have that nice sense of order. In a liquid, our particles are tumbling over one another. Okay, and then finally, in a gas, we're going to see that the particles are sparse. The word sparse means few and far between, and they're all over the place because they are moving very quickly and they are bouncing off the walls of their container. Okay, what would that look like on ALEKS? Well, a solid would be represented something like this. Okay, we see this orderly packing of our particles together. They're all touching, they're organized like little soldiers. That would be what a solid would look like. Okay, a liquid, on the other hand, would look something more like this. So we see the particles close together, touching each other here and there, but they lack order. Here we don't have, we can see that if we were to put the liquid in a glass, that it would conform to the shape of our container. All right, lastly, we have a gas. Okay, our picture for a gas won't have as many particles in it because there's a whole lot of space in between. Now, what ALEKS does, besides these drawings, they also give you some red herrings. Okay, so for example, you might see drawings that look like this. Okay. All right, so what we're starting to see here is this looks like a very orderly picture. Okay, everything is just the way it's supposed to be. Everything's tightly packed, neat, and orderly. However, we no longer have our model of SO2. We don't have these Mickey Mouse shaped particles. We have sulfur atoms together, and we have oxygen atoms together, but they are no longer forming the compound sulfur dioxide. Okay, so that's pretty much never going to be the one that we're looking for. And they do red herrings like this. They'll put in drawings. You have to pay attention to the details in the model. And one of the next generation science standards is about students learning to use models to represent ideas, because that's what we have to do in science. Part of our science communication is being able to interpret someone else's models and being able to make models that other people understand. Visual models are just one kind of model, but it is important to understand these. Okay, well, I hope that will help you with this type of problem on ALEKS.